In the previous section, we looked at problems where W is equal to g of x, and we would find the CDF of W, and perhaps take a derivative and find the PDF. And the tricky instances of these problems were ones in which the function g of x had flat regions that resulted in W being a mixed random variable. In this section, we don't focus so much on mixed random variables, but instead we look at the case of, of functions of two random variables. So our situation is we're interested in W as g of x and y, and we want again to find the CDF of W and the PDF of W. And the key to finding this CDF will be an integration over the XY plane. So once you get into the details of this integration, it's mostly calculus, but we'll do a couple of examples here to demonstrate the basic ideas. The basic method derives from this theorem, which just says that for any x, y, if you want to find the CDF of W, which is just the probability W is less than W, and this is just the probability that this function g of x and y is less than or equal to W, all you have to do is identify the region on the xy plane where this condition holds and integrate the joint PDF over that region. So specifically, you imagine, oh, maybe there's some region in here where g of x and y is less than or equal to W. And then the calculus of the problem is that you identify this uh, region. It's this set of points in the pink. And then you do some tricky calculus to integrate the joint density over this region. So the formulation is simple, but when you go to do this integration, it tends to be a little bit tricky. A bunch of good examples come out of looking at problems where W is the maximum of x and y. And we've seen the maximum before, but now we're going to generalize kind of our understanding of how you find probabilities related to the maximum of a pair. So in this problem, we have the CDF of W. We can always start and write it's the probability W is less than W. And that's the probability that the max of x and y is less than W. And then, of course, this is the key step in solving any problem related to the maximum. The maximum of x and y is less than or equal to W if and only if both x is less than W and y is less than or equal to W. So this probability is probably x is less than or equal to W and y is less than or equal to W. And in terms of calculus and integration, we have a situation like this. We have the region y less than or equal to W is all of the y values below the blue line, which is just y equals W. And then we have all of the x's to the left of the red line. And this red line is just the x's equal to W. So this corner point is indeed W comma W. And our theorem says we need to integrate over, over this whole region. And if we set up our integral, this is simply going to change pen colors. The integral of x's from minus infinity to w, and y's from minus infinity to w, and you integrate the joint PDF. And since I said that this is the integral of y's from minus infinity to w, then I should probably write dy first, then dx after. But in fact, in this case, without any more problem-specific information about the PDF, you could write it either way, and both are fine. So now we'll do an example of finding the PDF of W equal to the max of x and y. And we'll choose a region where the PDF is constant, but the region's not exactly a perfect square. It's kind of a rectangle. The x's are between 0 and 5. The y's are between 0 and 3. Let's say you have a situation like this. The x's, here's x, here's y, and there's a box with 5, height 3, and in this box, the CDF of x and y is 1/15. So the integral of this, PDF, the integral of this PDF integrates to 1 over the box. And the theorem from the previous slide says that the CDF of W is equal to the integral minus infinity to W minus infinity to W joint PDF dy dx. But the integration over this kind of a region is complicated because of the way it intersects this box region. So for instance, if we think about a W that is less than 0, then you have to extend this axis, and maybe you think about a W here. This is W, this is W, and your region of integration would be this region here, right? And what we see is that over this region, the PDF of x and y over this region is 0. It's part of the 0 otherwise region. So for instance, for W less than 0, we can conclude that the PDF of W equals 0. To move a little faster, we're going to do the rest of this problem using the slides from the book, which convey the other cases in a nice simple way. So the first cases to consider is W's greater than or equal to 0 and less than or equal to 3. So this is an example is depicted here where W is maybe about 2.5. And the region of integration is then given by the theorem, goes over all possible x's and y's less than or equal to W. So it's nominally this region. But when you set up the integral, you realize that the PDF is non-zero down here, and the PDF is, the PDF is 0 down here, and the PDF is 0 over here. So in fact, the region of integration for that we care about just has these limits. And the result is that the limits are from 0 to W for the x-axis and for 0 to W on the y-axis, corresponding exactly to this box. And when you do the integration, you get w squared over 15. The next important case is if w is greater than 3, but less than or equal to 5. So for example, in this depiction down here, w is about 3.5. And in this problem, the uh, the WW corner point is up here, and nominally, the theorem says we would integrate over all x's and y's in this lower left box. But in fact, the PDF of x and y is 0 in here, and 0 over here, and 0 down here. And the result is we have an integral where we integrate y from 0 to 3. That's the upper limit of this box, 0 to 3. And we integrate x from 0 to w, corresponding to this region. And that gives us the integral over this gray and soon to be with my highlighting pink box. And doing the calculus is fairly straightforward. And we get a nice answer, w over 5. And the difference here is that for w between 0 and 3, the CDF grew quadratically, and that's because um, the CDF was in proportion to this area of the box that's growing like w squared. But in the second case, now as w grows, right, the size of this box is actually equal. The area is 3w, and it's growing linearly. The area of the box is growing linearly with w, and so the CDF grows linearly. So this section has one more example that's perhaps even trickier than the last one. In this case, we consider w as the ratio of y over x. And once again, our goal is to find the CDF and PDF of w. Problems like this tend to be very tricky, particularly if x can be positive or negative, then you have trouble with the sign. However, in this example, we have one pretty good simplification. It's that the joint PDF of x and y is is positive only for both x and y positive. So this x in the denominator will always be positive, and it'll simplify things a lot. In fact, another element to making this kind of a tractable problem is the structure of this joint PDF. If you look at it carefully, you'll realize that the joint PDF of x and y can be written as lambda e to the minus lambda x mu e to the minus mu y. And you see that this is really a product of exponential PDFs, fx of x, fy of y, where x is lambda e to the minus lambda x greater than or equal to 0, 0 otherwise, and y is equal to mu e to the minus mu y greater than or equal to 0, 0 otherwise. And the product of these two gives us our joint PDF. So in fact, the problem we're solving in finding the PDF of W is finding the PDF, the ratio of two independent exponential random variables, but they're not identical exponentials. They have different mean values. So the problem says find the PDF, but of course, we always start by finding the CDF of W. And this is the probability that y over x is less than or equal to W. And now we can rewrite this as the probability y is less than or equal to wx by multiplying both sides by x. And here's where we really exploited the fact that the x has to be non-negative. If somehow we had a different random variable where x could be negative, you wouldn't be able to just simply multiply through by x because it would depend on whether we were looking at x's that were positive or negative. We'd have to do some tricky conditioning. So now the rest of the problem is really just calculus. We have x, we have y, we draw a line, which is y equals wx, and we realize that we're interested in the y's below this line, but because y has to be non-negative and x has to be non-negative, we're integrating over this triangle, but of course this triangle is going to kind of grow. It's not bounded by any limit. It goes to infinity both in the x and y directions. So our limits of integration in this problem will be x goes from 0 to infinity, and uh, and uh, and then y goes from 0 to wx, and we write in lambda e to the minus lambda x mu e to the minus mu y dy dx. So the rest of this problem is just calculus, and the textbook is as good or better at calculus than I am. So let's look at the solution. So in the solution, we factor this joint PDF. We factor out the lambda e to the minus lambda x. We integrate over the mu e to the minus mu y. That's pretty straightforward. And then we do two integrals of two different exponentials with the x, and you do a little bit of work and you get this expression. This expression is a kind of a disreputable random variable. In fact, it's an example of W is called a Cauchy random variable. And for instance, the reason it's disreputable is that if you go and try to calculate E of W, the expected value, you in fact get infinity. This uh, the PDF of this W doesn't go to zero fast enough as W gets large. So if you want to test whether you've got the hang of this, you should try to take this quiz. The next two slides after this have the solution. But see if you can set up the limits yourself and do the calculus. And if you follow the basic procedure we've outlined, everything should go fine.